Good morning, everyone. 10 people. Where is everybody? All right, there's 11. I know people usually come filing in a few minutes late. Anyways, good morning. Hopefully those who come in late will see this posted in the recording. If they actually go back and watch the first couple minutes, please and thank you. But remember, the assumption is always that when we finish a section, that homework is due within exactly a week, unless stated otherwise. And again, I'm pretty good about saying those due dates in here, but if you come late or leave early, you might not see it. So you need to remember that assumption. And those due dates are always updated in my math lab. 1.5 was listed incorrectly until this morning, and that was because of our snow day, and I put snow in quotations with my fingers that you can't see, because that was not a snow day. That was a that was a what the heck day. Anyways, let's not waste any time. We've got a lot of material in 1.5 to get through. Per usual, I'll be in the chat in a few minutes if you have any questions along the way. But yeah, we're going to finish 1.5 today, and then next class we'll start 1.6.
We are picking up where we left off in 1.5, quadratic equations. As a reminder, there's a solid amount of factoring required with these things. There'll be a solid amount of factoring all semester long, not just with the entire point of solving a quadratic equation. We'll have other reasons that we have to factor, as we will see. We said that there's three primary methods for solving these quadratic equations: solve by factoring, which we discussed fully, and which we also went over the various factoring methods that we have for this course. And I said that if you have a method that works outside of what we discussed, you're more than welcome to use it as long as it works. The quadratic formula, which we're actually going to do last, and the reason we do it last is because in spirit it comes from completing the square, which we have not discussed yet. We're about to. The thing that we discussed before completing the square, though, is this thing known as the square root property. And this is going to be a common issue throughout the semester. It's going to be an issue in later math classes if you go into calculus. It's when you have something like x squared equals 16, and this is a really simple one. Or it could be x squared equals -4. Or boiling down something to a parentheses squared equal to a number. Whenever you can get this type of scenario, anything squared equal to a number, the idea is that the opposite of something being squared is a square root. So if the squared thing is isolated, you take a square root to get rid of it. And then the rules of algebra state whatever you do to one side, you do to the other. So you take a square root on both sides. But this little plus or minus, we discussed the idea of a loss of sign, because when you square a negative, you get a positive. So x squared equals 16, just looking at that equation, a lot of people will instantly know that 4 is a solution, but they won't think about the fact that -4 would also solve it, because squaring the negative gives you a positive. So it's that reason alone that we need this plus or minus. Now, this is when we're dealing with even powers. If we're dealing with an odd power, there's no plus or minus. So if you had something like a cube root equal to a number, you could, I'm sorry, I said that incorrectly. If you had a cube equal to a number, you could take cube root of both sides. If you had something to the fifth equal to a number, you can take a fifth root of both sides. Technically, there's more complexity in algebra to that than what I'm stating, but we don't need to get into that layer of detail. But it's when you have an even power that this plus or minus is necessary. And I mentioned, and I try and mention this over and over and over because it's such a massive problem, you cannot forget this plus or minus when it's necessary. You will be getting answers wrong if you forget that plus or minus. And this is a very common problem. So you need to write that down 50 times, say it 50 times, have someone else say it to you 50 times, watch this video 50 times until you get that plus or minus stuck in your head. And I'm not trying to be discouraging. It's just a fact of life. We do things wrong before we do them right. Guess what? Been there, done that, bought the t-shirt, as they say. So we saw a couple examples of this square root property. Take a plus or minus square root. I have the isolate the x squared, take a plus or minus square root. Isolate the x squared, which was already done, plus or minus square root. Isolate the thing being squared, plus or minus square root. When you have square roots you can't take completely, try and break them down. That is necessary as well. If you left this as a square root of 8, it would be marked wrong in my math lab. And on homework, it's wrong. You got to do it again. Test, if you point it out and you have work that's shown in documents, and you point it out, I can maybe give a point or two back. All right, and that was the end of the notes that we got to so far. So we have to talk about that square root property before completing the square because, well, it's a part of completing the square. Completing the square. So very very specific set of instructions. And if I do that, it's one single line. Okay, cool. So first, move the constant to the opposite side of variables. You need your variable terms on one side and you need any constant term on the opposite side to do this method. Now, this is kind of the odd man out. With factoring, you want everything on one side. With the quadratic formula, you want everything on one side. So this is already the first instance where completing the square is a little weird. We want the variables on one side and the constant on the other. So that's a little weird, but practice makes perfect. Second step. And this is an if. So this isn't necessarily a step, it's an if step. If the leading coefficient is not 1, at all terms by it. So you're going to be taking some giant leaps of faith with me and trusting me that this works. As we do an example, I'll kind of explain why it works. But the good thing is that it works 100% of the time. It's just some mathematicians hundreds of years ago figured out this pattern. Excuse me. And, you know, they may have taken 100 or 1,000 or 10,000 different attempts to find the right pattern to make this work. But once you find it and it works, there you go. It's kind of like finding a you know, medicine or a antidote or something like that. You have to test a bunch of different things, and they're wrong, 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 and then eventually get it right. All right, third step. So after you've done that, and it would be both sides dividing by whatever the leading coefficient is. So this method hinges on not having a number in front of the x squared. So step 2 is, hey, if there's a number in front of the x squared, divide everything by it. All right. Then to the side, so this is going to be some side work, kind of like when I was factoring, if the last number was a -6, I split it into 1 times 6 or 2 times 3 to the side. So side work, to the side. Take half of b. Oh, and I have this written previously. I'll write it again. It's the top of completing the square after this step. Take half of b, then square the result. Each of these values important. All right, so we're completing the square on, and I'll make this look nice and pretty. AX squared plus BX. Let's see. So not underlined for that part, thank you. So completing the square on something like ax squared plus bx plus c. So again, the a, b, and c are just the coefficients or the constant coefficient at the end. So that's what I mean by to the side. You'll take the number in front of that x, whatever number you have in front of the x. Now, I don't necessarily mean, and this is where things are a little misleading, if you actually do step 2, this is no longer going to be b. So just take half of the number that is currently in front of the x. That's what I mean. That's what I mean by that. All right. Fourth step. Add the squared value both sides. Again, leaps of faith here. Then what will happen 100% of the time, this is a guarantee if you've done all of this correct, the LHS, which stands for left hand side, RHS would be right hand side. Those are abbreviations I'll use occasionally. So left hand side. The left hand side is now a perfect square trinomial and has the factored form. I'm actually going to have to write this out with the pen. X. Now I'm going to do something kind of weird. Plus or minus, and then I'm going to write this, the halved number, and then squared. This is the factored form. Now, when I say the plus or minus, you're going to take on the sign of whatever was here. So if this was a plus, then it's a plus here. If this was a minus, then it's a minus here. This is not the plus or minus that we were just using for completing, for the square root property. That comes next. All right, step 6. Apply the square root property. Means take the plus or minus square root of both sides and solve. 6 steps that feel very arbitrary, that is just a pattern that is guaranteed to work, and it all has to do with this thing called a perfect square trinomial. So I'll come back to this in a second if you haven't finished writing, but I want to go back. Oh, it was in the factoring document. That's not a problem. It's right here, except I didn't save it. So I'll just remind you of what I'm talking about, what a perfect square trinomial is. So a perfect square trinomial, not PTSD, PST, a perfect square trinomial was the thing like when you have x squared plus 2x. That's not what I want to do. Not x's. I'm sorry. I was not intending to write this. I was intending to pull it up. Ax squared plus 2abx plus c. I mean plus b squared, not c. When your leading coefficients look like this, you can factor it like this. Ax plus b squared. Or if it looks like this, ax squared minus 2abx plus b squared, it turns into ax minus b squared. These are factoring formulas that we don't use too often unless you are dealing with fractions. That's about the only time I would ever personally use the perfect square trinomial factor forms. Besides just this automation right here. This is automation. You will not have to think about factoring. It is always going to be one of these. And it's always going to be just an x in the first spot, a plus or minus based on the original sign of the middle term, and then the halved number. That's what this is saying here. This is the halved number. So remember in step 3, I said to the side, take half of b and then square the result. Each value is important. The squared number is what you'll add to both sides of the equation because it sets things up. And then when you actually go to factor it, it is automatically going to be that halved number right here. And we will see that kind of happen when we do an example. Okay. Excuse me, I'm a little stuffed up. We are not going to do all of this at once. Example, what are we up to? 3. Find out what you would add both sides by completing the square on these terms. So this is kind of an interesting example in that my pen has died. There we go. X squared plus 12x. This is just us trying to focus on the first 4 steps. That's all we're focusing on right now. We're not going to focus on step 5 or step 6. Just the first 4 steps. And not even really the first 4 steps. It's more just steps 3 and 4, to be honest. That's all we're focusing on, this halving and squaring. All right, so to the side, you take half of the number in front of x. That's what that says. Take half of the number in front of x. So we take the 12 and we half it, which is 6. Then what we do is we take that value, so we take this 6, excuse me again, and we're going to square it. So we take the 6 and we square it, and 6 squared is 36. That's all I'm asking for this problem. So find out what you would add to both sides by completing the square on these terms. So if this was x squared plus 12x equals to 15, you would be adding 36 to both sides. That would help you create your perfect square trinomial. If you added 36 to that, you would create a perfect square trinomial. Before we do B, what I'm saying here is x squared plus 12x if you just put a plus 36 next to it. This is 100% of the time after you do that addition, a perfect square trinomial that has a factored form that looks just like this. It would be, in parentheses, squared. You would have an x here, because this was a plus, this is a plus. And then that's the halved number. The halved number was the 12 divided by 2, and that's 6. It's x plus 6 squared. If you don't trust me, go through and do the old school factoring. Find the factor pairs of 36 to add to 12. Well, 6 and 6 add to 12. So you would go x plus 6 times x plus 6, but x plus 6 times x plus 6 is really x plus 6 squared. So kind of a special note, x plus 6 squared is really x plus 6 times x plus 6. But we want to get in the habit of writing things in the more compressed form, because we might have a fifth exponent, and then it's x plus 6, 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 and that's a lot of them. All right, B, x squared minus 7x. So our side work, we take the minus 7, since it's negative, and we half it. Half of negative 7 is, well, it doesn't reduce as a fraction, negative 7/2. Yes, it's negative 3.5 as a decimal. Please don't write it as a mixed number of negative 3 and 1/2. That is awful for factoring. But the point is, we take this number and we square it. Now I'm going to do this wrong first. This is wrong, 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 wrong. Why is this wrong? Because we're supposed to be squaring this entire fraction and the negative. This is only squaring the 7. It's not even squaring the negative. It's definitely not squaring the 2. Now it's right. Make sure you're wrapping fractions and negatives in parentheses when you want to square them like so. How do we square fractions? Square the top and bottom independently. Negative 7 times negative 7 is positive 49. 2 times 2 is 4. So what would we do to make a perfect square trinomial with that? We would add 49 fourths. And here's where things get interesting. What I'm saying is that you would make this x squared minus 7x plus 49 over 4. Now, if I asked you to factor this trinomial right here, I would actually never expect any of you to know the answer without having done this, because we don't really factor things that have fractions in them typically. It's very atypical. But here's the beauty of this. No matter what this number is, fraction, decimal, whole, whatever, because we did this process, we know that this number we acquired by halving the negative 7 and then squaring it. The factored form is automatically this. It's a parentheses squared with an x first, and then what was the half number? This negative 7/2. So that's what goes next. Negative 7/2. That is one way we can factor things involving fractions. Now, they again have to be a very special format, but when we're completing the square, we are literally creating the special format. So this, the halving and the squaring, what's going on here? Why are we really doing that? The form of this right here, this middle term with the formula, if you actually memorized it, has this 2. So this number is basically double what would have been here. And then because this was originally just a b, to get the actual number that goes here, you have to square it. So we have to get rid of the 2 and we have to implement the squaring. So we half it to get rid of the 2 and we square it to make it be a b squared. That's the idea there. I want to mix up these little lines. I don't want those saved there. Thank you. So that is our ultimate list of instructions for completing the square. The first steps are to set up something to make this automatic factored form. Then once you have something squared, it'll be equal to a number. And whenever you have something squared equal to a number, you can take the plus or minus square root. Thank you for that message. Appreciate it. So let's try this out. And we're going to do these examples. I have 2 sheets of completing the square examples, not that you care. And I kind of pick and choose which ones I do on the fly. I'm not going to have enough room here, so I'm going to keep having to kind of flip back to this list of instructions. Or maybe I'll copy paste. What just happened? I must have been on eraser. Select. If I copy paste that, will the other thing stay? does. Okay. Don't want that. I don't want that. All right. Example 4. Solve by C.T.S. Which is the abbreviation for completing square. Solve by complete the square method. Now, on a test, if I tell you to solve by completing a square, that's the way you're supposed to do it. If I tell you to solve it by doing the quadratic formula, that's the way you're supposed to do it. Now, admittedly, if you get the answer right, I'm not going to go back and check your work to make sure you use the right method. However, if you got it wrong and you said, hey, Mr. Beckner, I think I did most everything correctly, can you go and check my work? If it says to solve by completing the square and I see that you did quadratic formula, I will not give you any partial credit because you didn't follow instructions. This is not the type of instruction I generally do. It's pretty rare. The reason I do it in this instance is because both completing the square and the quadratic formula are good methods. A lot of people will be stubborn and don't want to complete the square. They say, I learned the quadratic formula, I'm just going to stick with it. But there are times when completing the square is actually easier, and I will discuss that after we've done both types of problems. So it's important to learn both. Also in higher mathematics and calculus, there are times when you have to complete the square on something that's not solving an equation, and a quadratic formula, because it's not an equation, wouldn't actually help you. So completing the square is an important method to get your head around at some point, not just for equation solving. It's a bigger picture item, believe it or not. All right, rambling over, let's do x squared minus 8x plus 3 equals 0. Okay, so the idea of completing the square is that the constant has to be on the opposite side of the variables. So the first thing you're going to have to do is subtract 3 on both sides, which will give us x squared minus 8x is equal to negative 3. I meant to be in blue, but that's okay. Doesn't matter. Then, if the leading coefficient is not 1, divide all terms by it. I will go ahead and spoil this. Any test question I give you on completing the square, you will not have to worry about step 2. I'm not making that promise in homework. I'm saying if I give you a completing the square problem on a test, I will give you a leading coefficient of 1. Do you want to know why that is? Because me personally, what I would advise is if it didn't have a leading coefficient of 1, especially if the other numbers were odd at all, I would never, ever personally complete the square because it sucks. I would definitely do the quadratic formula for that. So the even and oddness of the numbers is one of the reasons one method can be better than the other. Why would an odd number complicate things? Well, let's say this was a 2 and you had to divide everything by 2. This negative 3 would now be a negative 3/2. Now you've got a fraction in this bigger picture item. It's just complicating things. Quadratic formula is not going to have that complication. Now you might say, well, okay, well, why don't I just always do the quadratic formula? Because there's times in completing the square is easier, as I will discuss. All right, rambling aside, step 3, to the side. So going to the side, we take half of the number in front of x and then it's squared. So we're taking this negative 8. I thought I hit blue. Definitely want blue now. We take the negative 8 and we half it, which would give us negative 4. Then we take that result and we square it. Because it's negative, I definitely need to wrap it in parentheses, which would give us a positive 16. This is what I call the F number, because it's the factor number. This will come into play last. The 16 is what we add to both sides. So our x squared minus 8x, we're going, and then equals, I'm gonna leave some space, negative 3. We're going to add 16 to both sides. We're on step 4 now. Add the squared value, which was this, to both sides. Not the halved value, that won't work. This is the only number that makes that perfect square trinomial happen. It is literally the only number. Halving and squaring the middle term makes magic happen, mathemagic. Simplify first, of course. X squared minus 8x plus 16 equals negative 3 plus 16 is 13. Now, the left-hand side is now a perfect square trinomial. X squared minus 8x plus 16. Yes, you are most certainly welcome to go through and do the factoring. Factor pairs of 16 that add to 8. Well, 1 times 16 adds to 17. No. 2 and 8 adds to 9. No. 4 and 4 adds to 8. Boom. But you got to make them add to a negative 8. So it's negative 4, negative 4. But now your factored form is x minus 4 times x minus 4, which is really x minus 4 squared. You can certainly go through that process. Or you can just remember what your teacher suggested, that the left-hand side is automatically factorable, and the form is always automatically, in parentheses squared, with an x in the first slot, and then the half number including its sign after that. The half number being the negative 4, not positive 4, negative 4. That's why I call that the F number, the factor number. Now we cannot forget the equals and we cannot forget the 13. Nothing magical is supposed to happen to the right side. That's just a byproduct. Then we're at step 6, apply the square root property, which means to take not just a square root of both sides, a plus or minus square root of both sides, but only a plus or minus on the number side. So square roots and squares cancel, so the left side is just x minus 4 equals. We don't know the square root of 13. We cannot break it down, so that's just plus or minus square root of 13. And then solve, just do whatever you have left. We don't really even care right now what this right-hand side is. We're just focused on the side with a variable. It says x minus 4, which means we're supposed to, we're supposed to add 4 to both sides. Remember, when you have this plus or minus, you need to get in the habit of leaving a space there, because if there's terms to move, you have to put it in front of it, not after it. Putting it after could imply the plus or minus is going with it, and it doesn't. So the answer is x equals positive 4 plus or minus the square root of 13. You would have never found that answer being factoring of rational numbers. Notice I said via factoring of rational numbers. We are going to actually learn a way that we could have factored this later in the semester, and it actually just uses the answer we got. I now can make a factored form knowing the solution, but let's not do too many things at once, right? Just foreshadowing. Before we do B, let's reiterate what we've done, because I know a lot of this feels random. You've got to practice this on your own. You've got to pay attention. You've got to understand the reason we're doing these things. Our goal, this is our goal. We want to get to something squared equal to a number so that we can very simply just take a plus or minus square root of both sides. That's why that was our big picture goal, so that we can break this down in a very simple way. To achieve this goal, we need to have 3 terms that are a perfect square trinomial. They have to turn into this parentheses squared, which this definitely was not of that format. It may be factorable, but not of that format. Now, spoilers, this was prime. There's no factors of 3 that add to 8. 1 and 3 add to 4. So this was prime originally. The entire thing is still prime. We just were able to factor a chunk of it. So to get to that goal, we need the variables on one side, constant on the other. Then because of that, the 2b and the b squared kind of set up. Sorry, I'm coughing a lot today. I apologize for this. That's why we half and square to the side. And those magical numbers, one of them is what we add to both sides to fit that perfect form. And the other one is the number that'll go in the factored form. Okay, another one. X squared plus 6x plus 11 equals 0. This is not too bad for completing the square. How do I know that this is not too bad? How do I know that this is a problem that me personally, I might want to tackle it with completing the square instead of quadratic formula? Reason 1, there's no number written in front of the x squared, which means I don't have to divide that out. It means it's a 1, it's perfect. Reason 2, there's no fractions anywhere here. Now, if there was, say, a 3 here, when I divided it out, I would create fractions. That's an ultimate problem. Having a number here isn't the end of the world as long as they all divide perfectly. But if they don't divide perfectly, I would never suggest completing the square. I'll show you, I'll start an example that sucks, but I won't finish it. Okay, so first we got to move the 11. We got to have just the variables on one side to make that magic happen. Then to the side, we take the current number in front of the x, which is a 6. We half it, which is 3. Then we take that value and square it, which is 9. After you square it, that should always be a positive value. You should always be adding a positive value. Even if the half number was negative, squaring it will make it positive. I guarantee it. So this is what we add to both sides. The 3 will come up later. That's the factor number. So our x squared plus 6x equals negative 11, leaving space. We're going to add 9 to both sides. Why? Because this is now a perfect square trinomial. It is automatically factorable. You don't even have to think about the process of normal factoring. You just make parentheses and square it. You put an x in the first spot, and then the half number goes after the x. This was a 3, which means it's a plus 3. Then equals whatever the right side turns out. Negative 11 plus 9 is negative 2. And this is exactly what we wanted. This was our temporary goal. We wanted anything completely squared equal to a number. See, when you have here, oh, I've got an x squared, so I'll just take a square root of both sides, plus or minus even. No, that would be wrong. You can only do that process when the entire side is being squared. That's when we can do our plus or minus square root of both sides, plus or minus on the number side. Why do we do that? Because square roots and squares cancel. Algebra, especially equations, is generally all about unraveling something. So that left side is now just x plus 3, then equals plus or minus. I don't know the square root of 2, but because we have a square root of a negative, we know in here that we need to pull out an I. I much prefer it in front of the square root. You can put it after, just make sure it's not in the square root. Only one more step. We're focusing on this, x plus 3. We got to move the plus 3, so we subtract 3. That must go in front of the plus or minus for notation's sake. It is not acceptable after it. So x equals negative 3 plus or minus I square root of 2. You are definitely not going to get that solution by factoring at this point. Traditional factoring is never going to find you that solution. Nobody knows. I'm not going to say nobody. Nobody at our level can factor x squared plus 6x plus 11 and know that it's x plus 3 plus I square root of 2 times x plus 3 minus I square root of 2. You're probably wondering what the heck I just said. So ignore it for now, because like I said, we can't do it. In order to factor this original thing, you actually have to do this process, have the solution, and then you can do that. It's a trick. There's a lot of tricks in pre-calc. We're going to learn a lot of tricks to kind of circumvent bigger issues, one of which I just mentioned. Factoring numbers using imaginary numbers. I said factoring numbers, factoring polynomials. All right, so what's a problem that this would suck on? So I'm going to start this one. I will write the answer. I'm going to say C, finish on your own if you like. Let's go with 2x squared minus 20x minus 5 equals 0. So I don't like this one for 2 reasons. Reason 1, I got a number in front of the x squared. Now that's not the end of the world. That just means I got to divide everything by 2. But the real reason that it sucks is about to peek its head after I do that. Now I can go ahead and divide by 2 before moving the 5 technically, but let's follow this specific order. So 2x squared minus 20x is equal to 5. So it's at this point, because the leading coefficient's a 1, that's not allowed, you divide everything by 2. Once again, I could have done that first step. The order of those 2 steps is arbitrary. Okay, so a little more work. Not the end of the world so far. But this is going to give us x squared minus 10x is equal to 5/2. And it is this complicates things. It sucks. because we're going to have to be doing that adding of numbers and square rooting involving a fraction now. It's ugly, it's muddy, you can do it, it's just muddy and more complicated. But when you go and divide by 2 and square it, you'll get 25, you'll add 25 to both sides, you'll have to take 25 and add 5 halves. Now remember, you are supposed to know how to add and subtract fractions in here, so don't think you're going to get away from that skill completely. I'm just saying that's why this sucks. And then you'll have square roots of fractions and you'll have to break them up, blah, blah, blah. End of the day, the solution ends up being x equals 5 plus or minus the square root of 110 over 2. The 2 is not in the square root. So finish on your own if you would like to. This is not an easy problem, but I just at least wanted to show you when that would suck. So me, if I were a student and I was an awesome student and I knew that I could, if on the test it said solve by completing the square and it was this problem, I'd be like, well, Mr. Beckner said if I get the answer right, he's not going to care which method I did. So I'd go, nah, dog, I'm gonna do the quadratic formula on this because I see fractions are going to pop up. So that's bad. When there's no fractions, I love completing the square. I love it. It's great. It's, I would say more often, actually more efficient than the quadratic formula. But those steps, again, I know they feel arbitrary. I'll even admit when I was a student and I learned this the first time, guess what? I did exactly what I told you you could do. I ignored the instructions. I'd quadratic formula it and get the answer right anyways. And my teacher was kind of similar to me. They didn't care about the method as long as you get it right. But again, you get it wrong, that's when I'll go and say, you didn't do the right method, so I can't give you partial credit. So if you're gonna do a method they say don't do, the point is, make sure you can get it right. All right, so finally, let's get to what, again, I know most people prefer one Pre-Calc 1 class. One time about 5 years ago, it was really interesting. I would take a vote and I had more students say they like completing the square. It was unbelievable, but that's the thing about humans. We are sometimes unpredictable. So again, this is for that, and I'm just gonna write this with a pen, it takes too long. ax squared plus bx plus c equals 0. So if you took this right here, and back in the day when we had a little more time for lectures, if you subtract the c on both sides, and then you'll have ax squared, then you divide all the terms by a. You're just doing the completing the square method without numbers in place, so you have to deal with these a's, b's, and c's constantly, and it gets ugly and muddy. But if you keep doing that, and then the halving of the thing and the squaring of the thing, what you will end up with is the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. You better memorize this. You should admittedly have memorized this in a previous math class, and if you forgot it, rememorize it. You never get to forget this in Pre-Calc 1. You never get to forget this in Pre-Calc 2. You never get to forget this in any kind of calculus class. Yeah. You know, man, I don't want to make that joke in a recorded lecture. Dang it. Dang it. Okay, never mind. I have a good joke that goes with this, but it's not risque. I just don't want to say it in a recorded setting. 10 years from now, it'll be risque or something. I don't know. Times change, right? So negative b plus or minus square root of b squared minus 4ac all over 2a. There are so many opportunities to mess this up. People swap the b and the b squared. People forget the negative. People just do a plus or a minus, not both. People forget the 2 with the a. People forget the 4. People jumble up all sorts of letters. Instead of doing the all over, I'll see this. This is wrong. I'll see this, just the square root part over it. No, it's supposed to be that. All right, so let's try out the quadratic formula. Example 5, solve by QF, quadratic formula. A, we'll have x squared plus 6x plus 1 equals 0. plus, excuse me, 11, not 1, 11. Right? Yes, okay. The point was I'm doing B again, in case you didn't pick that up. I didn't mean to write 1. I have bad eyes. X squared plus 6x plus 11 equals 0. So here's one thing I'd suggest is that you go to the side or below or whatever, and you write down what your A, your B, and your C are, especially at first if you're kind of getting reacquainted with this, or if it's unbelievably your first time ever doing it. Establish what A, B, and C are. This is what you call plug and play, or some people call it plug and chug, because all you're doing is plugging numbers into a formula, and then it's arithmetic, arithmetic, arithmetic. If your arithmetic sucks, you're going to get answers wrong. If you don't memorize this formula, you're going to get answers wrong. But it is a simple concept in a pre-calculus class, just putting numbers in place. Circle goes in the circle, square goes in the square, pentagon goes in the pentagon, whatever. So just applying that formula. Let's back off just a little bit so we can still see it. Uh-oh. What happened? I think I hit save. I hope I didn't undo anything serious. That's fine. That's fine. That was not a problem. So x equals formula. Negative b. So b is 6, so negative 6. Watch out when b is negative. That's when people make mistakes. Plus or minus. Big square root of b squared, which is 6 squared, minus 4 times a times c. A is 1, c is 11, so times 1 times 11. All over 2a, which is 2 times 1. So there's our formula. There's us applying it. And from here, it's just arithmetic. That's all we're doing at this point. It's just arithmetic. So x equals negative 6 plus or minus square root of 36 minus 44, all divided by 2a, which is 2 times 1, which is 2. 36 minus 44 is negative 8. So we get x equals negative 6 plus or minus the square root of negative 8, all divided by 2. The square root of negative 8 we cannot completely take, but we can simplify it. So we go x equals negative 6 plus or minus. So we can write that as the square root of negative 4 times 2. You can break up the negative as negative 1 times 4 times 2 if you really like. We know the square root of negative 4 is 2i. So we still have this square root of 2 inside. This negative 4 gets pulled out as 2i. So that square root of negative 8 is now going to be 2i square root of 2. Then we have the all over 2. And I have warned you about this setup right here that we've just gotten to. Very often we're done, but if all of these numbers, all the outer numbers, the 6, the 2, and the 2, not this 2, if all of these 3 numbers have a common factor, you have to take a GCF out and reduce it, or just divide them out individually. I find that a lot of students much prefer writing it this way, negative 6 plus or minus 2i squared root of 2 over 2. They just do the divisions individually. So 2 goes into 6 3 times, 2 goes into 2 once, and into 2 once. We don't need to write those ones, though, in a denominator or in front. So that gives us our solution is negative 3 plus or minus I square root of 2. Now let's see if that's the same answer we got before. Negative 3 plus or minus I squared root of 2. So this was solving it by completing the square, which in my opinion is not that bad. There's no fractions. That's what makes it bad. There wasn't a number in front of the x squared, which is something that people just tend to forget about and they'll leave it. So it's not bad, but it leads to bad results often. So it wasn't too bad with completing the square, ultimately. It also wasn't too bad with the quadratic formula, but some people will mess up here. They'll stop and they'll say this is the answer, and that's wrong. Also, some people may have stopped here and not reduced, but it's wrong. Those two issues did not come up when we did it by completing the square. So that's one strength of completing the square. A lot of the arithmetic simplifications don't end up happening. But ultimately, if you're solving an equation, it doesn't matter which way you solve it, which is why I said if you can get it right, if my math lab says it's right, I won't care about the method. If it's wrong, that's when I'll say, all right, you got to focus, you got to at least learn one of these methods. But again, ultimately, you might think that you can just disregard completing the square. It has its uses outside of equation solving. And if I was a mean pre-calculus teacher, we would actually see that in here, but I take a different approach to that later, so it won't be an issue. All right, let's do one that we haven't done yet. 2x squared minus 3x minus 2 equals 0. Now, remember, you may have to do a few steps to get to this point. You may have a distribution or moving of terms, blah, blah, blah. I'm just trying to focus on the main idea of these. So everything's on one side. That's quadratic formula. It's completing the square that you need the constant on the other side. So our A is 2, our B is -3, and our C is -2. So plugging that into the formula, which I will scroll up so you can see it again. There we go. X equals, this is my favorite type of problem to do because you have to pay attention. B is negative, so negative B is -3. Sure, you can go ahead and write that as a plus if you're cool with it, but I'm being meticulous. Plus or minus square root of B squared, because it's negative, you cannot just do this. This is wrong, because that would be -9. You have to wrap it in parentheses, and it'll be +9. Then minus 4 times A, which is 2, times C, which is -2. You can wrap the +2 in parentheses if you like. It's up to you. And then over 2A, which is 2 times 2. What I had said is on test questions, if it says complete the square, but you solve by quadratic formula and get it right, you're demonstrating knowledge and an alternate method, and that's fine. The point was if you got it wrong and then wanted partial credit, I will not give partial credit if you don't follow instructions. That was what I was saying. All right, so x equals +3, the double negatives cancel, plus or minus square root of +9, because the -3 itself was squaring. Now here's where people make mistakes. This will be a mistake. Oh, 4 times 2 times 2, well 4 times 2 is 8, 8 times 2 is 16, so that's a -16. This is wrong, because you have a negative times a negative, which makes it a positive. Very easy to make that mistake. Guess what? Been there, done that. All over, 2 times 2 is 4. Well, 9 plus 16 is 25. So we go x equals 3 plus or minus square root of 25 over 4. Now this problem is easier. It's not a square root of -8. We're not pulling eyes out. We're not breaking things up. We know the square root of 25 is 5. So this is a colon just so I can skip going down a line. X equals 3 plus or minus the square root of 25 is 5, and then all over the 4. So another question. No, A was +2, and that's just 2A in the formula. Now, if the A was negative, there would be a negative in the bottom, and that is, I was going to bring this up after this example, but if your A is ever negative, there's a trick to make it positive. I'll show you that after the example, though. Now this, a lot of people say, all right, here's your answer, and then my math lab marks it wrong, and I go, yeah, that's wrong. It's not simple. It's partial credit worthy, but it's not this simple answer. Because look at the difference of the number after the plus or minus versus what we've seen the past few times. Square root of -8, you couldn't get rid of the square root. You were stuck with it, and you can't add constants, whole numbers and square roots. This is not a square root. You can do 3 plus 5. You can do 3 minus 5. So in this case, what you actually have to do is you must split this into the two cases. So you'll go x equals, just do this, 3 plus 5 over 4, and you'll go x equals 3 minus 5 over 4, or a comma to separate them, whichever. 3 plus 5 is going to be 8, so that's x equals 8 over 4, which is 2, so that's one of the answers. 3 minus 5 is negative 2, so that's negative 2 over 4, which must reduce to negative 1/2. So there are our two answers. So you'd separate those by commas in my math lab most likely. Pay attention to the instructions. So when you don't have any more square roots left over, you actually have to separate those two cases, the plus case and the minus case. This is in an unacceptable answer right here, 3 plus or minus 5 all over 4. If it was square root of 5, it would be fine. If it was plus or minus square root of negative 5, it would have been fine. But with no square roots, you must split the cases. What this means is no square root in the answer means the original problem was factorable via traditional factoring methods, the ones that we know. So A, you could not, if I told you to solve by factoring, you'd go, you're lying, Mr. Beckner, I don't know how to do that. And then I'd go, you're right, good catch. It was probably a typo. But if I could have told you to solve B by factoring. You can factor this via trial and error, AC method, box method, push and pull, whatever you're using, whatever you're calling it. Half of those methods are really the same thing, just different visual flares. So let's go back and look at some other examples. With the completing the square, neither of these would have been solvable by factoring because of the square roots. And again, with traditional factoring methods. But this problem would have been. So that's another case of, if you recognize that on a test in my math lab, you could get to the answer by not following instructions. If it was right, you'd still get full credit. If it's wrong, I'd go and look at your notes, and after you told me to, and I'd say, nope, sorry, you didn't follow instructions, so I can't give you partial credit. One more of these for the road. X squared. That negative thing I'm going to do after this, by the way, I haven't forgotten. Minus 6x plus 9 equals 0. Spoilers, this one's factorable. Spoilers, it's a perfect square trinomial. I will actually show that after doing the A equals 1, B equals negative 6, C equals 9. Again, make sure they're all on the same side before you go and label those. That is important. So we go x equals negative b, so negative negative 6, that happened again, plus or minus, big square root, b squared, which is negative 6, all squared, minus 4 times a, which is 1, times c, which is 9, all over 2a. 2 times 1, which wound up being 2. I'm going to try and save myself some space, so I'm going to go colon, so I'm over here. X equals, the double negatives cancel, so positive 6 plus or minus square root. That's a positive 36. 4 times 1 times 9 is 36. There's still the minus in front of it. There was not a double negative for that one. All over 2 times 1 is 2. 36 minus 36 is 0. 20 minutes. So that's x equals 6 plus or minus the square root of 0. Oh, interesting. All over 2. Colon, saying we're moving right. That's x equals 6 plus or minus square root of 0 is 0. All over 2. Here's the thing about adding 0, it does nothing. Here's the thing about subtracting 0, it does nothing. When you have a plus or minus 0, it does nothing. 6 plus 0 is 6, 6 minus 0 is 6. So splitting these cases won't actually do anything. 6 plus 0 over 2, comma, 6 minus 0 over 2. That's just 6 divided by 2 and 6 divided by 2. Colon, so x equals 3. This is what's known as a repeated root, a repeated solution. When we get into graphing polynomials, this creates implications. But I don't want to spoil too much of the fun yet and throw you off. So there's only one solution. That can happen. It happens because of this. Whenever the inside of a square root ends up being 0, the square root is 0, and then the adding and subtracting of 0 does nothing. The plus or minus is completely irrelevant. You can just toss it out at that point, and the answer is 6 over 2, which is 3. That's what leads to what we call repeated roots. If you did this by factoring, the x squared minus 6x plus 9 equals 0. Now, we didn't complete the square, so you might not recognize that idea of perfect square trinomial. So you take your factor pairs of positive 9, which are 1 and 9, or 3 and 3. You'll choose 3 and 3 because they add to 6. You'd make them both negative. Sorry for the tiny writing. And that would give us x minus 3 times x minus 3 equals 0. Setting each of those equal to 0 is literally the same thing. So when you add 3 to both sides, you get x equals 3 and x equals 3. It repeats. You don't have to write it twice. You really should only write it once. But the fact that it pops up twice, again, has implications, big implications, very important implications. And that's because the x minus 3 squared, if you were to do that plus or minus square root of 0, plus or minus square root, squares and squares cancel, you just get x minus 3 equals 0. So that exponent, when it's set equal to 0, is actually irrelevant. If you have x minus 3 to the 5 millionth, the solution is still x equals 3, as long as it's set equal to 0. Okay, here's a trick. Let's say, that looks like truck almost, trick. Let's say you started out with negative, and I'm not going to finish solving this. I'm making this up on the fly. I do not know the solution. I can find it, but that's not the point of this. Negative 3x squared plus 5x minus 7 equals 0. Let's say you have this. A being negative complicates things. It sucks. Here's what you do. Before you write it, A is negative 3, B is 5, and C is negative 7. Just multiply both sides by negative 1. So we'll take negative 1 times the left side, negative 1 times the right side. Which gives us positive 3x squared minus 5x plus 7 equals 0. Now your A is positive 3, your B is negative 5, your C is 7. You don't want the A to be negative, and this is why. I'll scroll back to this in a second. I got to go to the formula though. If your A is negative, your denominator is negative. Having a negative denominator messes up a lot of people because it changes the sign of the first thing, but it doesn't actually change the sign of the second thing. Remember, leaving negatives and bottoms is not acceptable in my opinion and in most real mathematicians' opinions. But because the plus or minus basically encompasses both scenarios, it doesn't change it to a minus plus like you might think. It just stays plus or minus. So it only changes one of the signs, which feels wrong, but it's right. Which is why I suggest if you ever end up in this kind of scenario, just multiply both sides by negative 1 or divide both sides by negative 1. An alternate trick is move everything to the other side. Add 3x squared, subtract 5x, and add 7. There's definitely more than one way to skin this particular algebra problem. All right. So we did 3 of these quadratic formulas. We did 2 completing the squares. We kind of started a third one, but I said it sucks. I gave you the opportunity to finish it later by giving you the answer, so you can confirm that. You could probably Google something, complete the square on this, and it might give you the list of instructions on that one problem, so to kind of give you an assist if the fraction throws you off. I mentioned something very important right here, that square root of 0 is 0, plus or minus 0 doesn't affect anything, which causes us to only get one solution. There are times where it's really nice to know there's only one solution without knowing or without needing to know the solution. There are times where it's nice to know whether the solutions are real, like this, x equals 3 is real, x equals 2 and negative 1/2, those are real, or if they're imaginary, like negative 3 plus or minus I squared of 2. This is us starting to get into the idea of what imaginary numbers are really called imaginary for. So this quadratic formula, what we're going to do is we're going to take this part right here, the part that's inside the square root. This one formula that you have to memorize, there's actually 3 formulas there. The quadratic formula being the first, what I'm about to call the discriminant, what I just circled in red, that's the second formula. And then a third formula we'll get later is going to be this part, everything else, the negative b over 2a. That's going to be a formula for later, but not yet. So let's just take the inside of the square root, call it d for discriminant. We're not discriminating, it's a discriminant. And that number, whether it's positive, 0, or negative, gives lots of implications. So the discriminant tells us how many and what type solutions the quadratic has. That formula is d for discriminant equals b squared minus 4ac. Once again, literally the same exact thing as what was inside the square root. So if I ask you to say, describe the solution types, that's not me asking for the solutions. Now solving it, you could describe the solution types with the solutions, but a lot of people mess up doing that. So when I ask you, what are the solutions like? Are they real? Are they imaginary? Are they conjugates? Is it 1? Is it 2? That's when you go to this thing. There's 3 cases to this. If the discriminant is positive, there are 2 real solutions. Real meaning no eyes. And I go back to that. What's happening? There we go. New space. If the discriminant is negative, there are 2 complex conjugate solutions. Remember, conjugate means a plus b, a minus b. The thing about imaginary solutions, they always come in complex conjugate pairs. So if I told you that 3 plus 2i is a solution, that automatically makes 3 minus 2i a solution. And it has everything to do with the discriminant. Third case, if the discriminant is 0, there is only 1 real solution. So in other words, when you simplify the number inside of the square root as much as possible, if that number is positive, you'll get 2 real solutions. Why? Because if the inside of the square root is positive, that means you're taking the square root of a positive. Imaginary numbers only pop up when you take square roots of negatives. So that is completely logical. If the inside of the square root is positive, you'll get real solutions. That's the first case. If the inside of this square root is negative, ultimately, that means you'll have to pull out an I, which means those solutions will be complex. Now, it turns out that complex solutions always come in conjugate pairs because of that plus or minus. That is part of the formula. If the discriminant ends up being 0, there's only 1 real solution, and I've already explained this before we even got to the discriminant in this example, because whenever your inside is 0, the plus or minus 0 is irrelevant. You can just get rid of it. When you split the cases, you get the same answer. That's why there's only 1 solution, and it's real because you weren't taking a square root of a negative. Again, these 3 cases are completely logical. I'm not going to tell you to memorize these cases. Half of you probably will. But what I would more suggest is that you understand the logic and reasoning to it. That's the important of pre-calculus. It's not just memorizing things flat out, which I know sounds ironic since earlier I said memorize the process of completing the square, but I did give you the logic and reasoning to it, didn't I? Because that's the type of thing that helps us when 6 months from now, we're supposed to do it on the fly, and we haven't done it for 6 months, so we didn't use it, we lost it, but if we have good logic and reasoning, we can go, okay, well, the goal was to get a perfect square trinomial. Perfect square trinomials had that 2 and the b squared in it. Those are the things we were trying to kind of backwards get rid of. Oh, that's right. So to get rid of the 2, we have it. To get the square, we square it. That's how we play with the numbers. Blatant memorization doesn't usually work for most people. It's how we learn things and then forget it 2 days later. So let's try this out. Example, what are we up to? I know there's a lot in this section. 6. Identify solution number, which means is it 1 or 2 solutions, and type, which means is it real or complex. A, 3x squared minus 7x plus 1 equals 0. Once again, they don't have to be all on one side. It doesn't have to be so neat and tidy. I'm just getting down to brass tacks because we only have so much time together. That time is coming to an end for the day after these 2 examples. So it's still a good idea to label your A, B, and C when they're in the appropriate locations. Watch your signs. Very easy to make mistakes with that. So our discriminant, that formula, which you don't really have to memorize as long as you understand it's the inside of the quadratic formula, which you've already memorized, right? Hint, wink, nudge. It's a 3 for 1. So b squared, that's the negative 7. I told you I love the negatives for the b squared. Then minus 4 times a, which is 3, times c, which is 1. So our discriminant is 49 minus 12, which is 37. Now, I don't care if this number is 37 or 59 or 2.7 or 1,000,001. What I care about is that this is a positive number. So the discriminant is positive. If the discriminant's positive, that means there's 2 real solutions. That's all we can say. I don't know what the solutions are. I did not solve it, but I can tell you there's 2 real solutions, and that has massive, massive implications to the graph, which I will illustrate after example B. X squared plus 2x plus 11 equals 0. Everything's neat and tidy. The A is positive 1, the B is positive 2, the C is positive 11. So our discriminant is, don't try and guess this answer based on the A, B, and C. You'll probably guess wrong. So b squared is 2 squared, then minus 4 times A times C, 4 times 1 times 11. So our discriminant is 4 minus 44. So our discriminant is negative 40. Watch your signs, which means the discriminant is negative. You can write the word negative, doesn't matter how you're saying that. The point is to make the analysis. Don't stop here. Without the analysis, that's nothing. It means there are, because it's not 0, there's 2 solutions, but because it's negative, they're complex solutions. They're complex conjugates specifically. My math lab might just say they're complex. They might not throw the word conjugate in. I have seen that change from publisher to edition to software. I can't keep track of every single solid detail, so that's why I'm giving you the beefiest answer, and you might have to do the lighter answer in my math lab. Special memo. If you can take the square root of your discriminant. In other words, if your discriminant is a perfect square, so if the discriminant turns out to be 4 or 9 or 16 or 25 or 36 or 49, that means that it's rational solutions which also means they're factorable. Rational solutions means the original problem would have been factorable. You don't have to solve it with the formula or completing the square. Remember, in the real world, 98% of problems aren't factorable. But if you looked at the problem, calculated the discriminant, and it was 49, you could go, hey, that problem's factorable. And maybe that says, all right, I was going to complete the square, but now I'm just going to try and factor it. Or I was going to do the formula, now I'm just going to factor it. So that's something that the discriminant can help you with. Maybe you're not sure whether the problem's factorable or not. Do b squared minus 4ac. See if you get a number you can take a square root of. Now, not with i's, a rational. Rational means no square roots. Remember, I is literally a square root. So if you go back to A, the discriminant was 37, that means they're irrational solutions. B, negative 40, means they're irrational. If I had done the discriminant for problem C, that b squared minus 4ac was 0, the square root of 0 is 0. Look, rational solutions. The b squared minus 4ac for problem B up here ended up being 25, which we know is square root, which is why the solutions were rational, which meant it would have been factorable. There's big picture implications with that. That is not something I'll test you on, but it's just another reason to be using a discriminant. Because I will say we're not going to use this a lot directly moving forward, but you might want to take the time to do it in some of the graphing problems because of its implications. All right, so last thing in the last couple minutes we have, let's throw up the three different cases. If your discriminant is positive, now this graph may be pointing up or down. I'm only going to draw them pointing up, but the point of this is that the graph crosses your x-axis twice. That's your two real solutions. When your discriminant, sorry for the ugliness of the axes, but I'm not going to take the time to redraw it. Not good enough. I have to redraw that. Touch and go, touch and go, touch and go. It's so close. Let me just kind of shade that in. There we go. Okay. This would be a case where the discriminant was positive 1. I mean, not positive 1, 0. Why did I say positive 1? Oh, I know why. Because I was going to say 1 real solution. Solutions to equations are interpreted as x-intercepts. And graphing these x-intercepts is going to be important. When your discriminant is negative, this is what your graph ends up looking like. And again, these graphs could point down or up, it doesn't matter. They won't point left or right because then they're not functions. This is not touching the x-axis at all. There are two complex solutions, i.e., they're not real, and this is why we call imaginary numbers imaginary. They are imaginarily touching the x-axis. There are solution values that have importance and implications, but the picture, it doesn't cross the x-axis. That is the aspect that's not real for imaginary numbers. That's it. They exist. They are tangible. They are in engineering and physics and science and chemistry and biology everywhere, in the ocean, in the waves, in the air. But graphing, this is the reasoning we call them imaginary numbers because it imaginarily crosses the x-axis. When it crosses the x-axis, there are real solutions. There's no I solutions to these first two. This one would have I's in the solution. All right. So this idea right here, we are going to go with in a later chapter. I'm just giving you the setup for it. I believe it's important to really tie everything together, so I like to. I know a lot of math teachers just regurgitate the material and move on, and they probably get one or two sections further by the end of the semester than I do. But I think that my students walk away with a larger understanding of how things go together. When I teach trigonometry, I teach that there's really only 4 things in trigonometry that you just do over and 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 over, just in bigger ways each time. But trigonometry really is just 4 basic concepts, extended as much as you possibly can.
All right, so that is it for 1.5. So again, you can see your due date on the board if you didn't catch it this morning. If you have any questions, please email me. Please keep up with your work. Please complete that prerequisite assignment. Remember that it's going to get you 5 bonus points on test 1. We'll start talking about test 1 due date maybe next Thursday, but we'll be doing 1.6 next, and that's going to take us about a class and a half to go through. Just a fair warning. Besides that, have a good weekend, everybody.